Okay, so it's time for memoization technique now for the coin change problem. And we already discussed all this stuff. Like, for example, if I go to the previous slides, if I can. So, wait, what happened? Oops. Open board and my docs. Maybe this one. Yes, let's open it. Okay, so we already discussed this by growing the tree, and we have seen that we have two methods, memoization and tabular. I explained tabular nicely, and we also coded both the method, both like uh, approaches where we can optimize the space in tabular method, but we haven't coded memoization yet. And memoization can be coded if easily we can code the recursive or the exhaustive approach. And we know this exhaustive approach. To refresh, I'll give a quick refresher, but with a really small example. Okay, so let's take rather just two coins, one and two denomination, and we have to make three. So how we can do that? We have 0 1, either choose, not choose. If I don't choose one, then we are left with just two and amount still remains three. If I choose one, then I'm left with still one and two, because we can reuse the coin, but amount will be reduced by one because we have choose one coin of amount one. And now again, choose, not choose. If I don't choose, we are left with nothing. Still amount remains three. If I choose, then still I'm left with two, but the amount becomes one now. Okay, because we have choose the coin of amount of denomination 2. Then again 0 1, and if I go this side, then obviously we are out of coins, and if I choose, we are at -1. Now this -1 indicates that mathematically it indicates that we can't make a coin amount 2 with with just the coin of denomination 2. Okay, this is what it indicates, right? And that's why we are getting -1. So it's not possible, because even this side we are out of coins and this side we are getting -1. So both these things are a not possible case. And we will see how not possible can be handled. But let's grow the tree as of now. Similarly, if I go and continue to expand, then if I don't choose, still 2, amount remains 2. If I choose, I'm left with both the coins, amount becomes 1. Again here, two cases, we are out of coins. And if I choose, then this is the perfect case, which is what we need. That when amount becomes 0, we know that we made it, and obviously we made it. As a common sense, we know that for in order to make amount 3 using these two coins, we need one coin of amount 1 or denomination 1 and one coin of denomination 2, right? Which will make it 3. So this is one of the valid path which will make it 3. And we also know there is one more valid path, 1 1 and 1, as a common sense. Let's see that. It will be here. So if we expand this now again, 0 1, then if I don't choose, I'm just left with 2, amount still remains 1. And if I choose, you can see now I'm left done with 0. So we have used three coins, one here, then one here, and one here of amount 1, all of amount 1, and it makes to 3, right? And now if you spot this, if you grow below this, it will be same as this. And this is where our repeated sub problems are, as we already seen. So that's a quick refresher. Now how to code out this? And we know that we need minimum number of coins. So out of this two, here we are using 2 coins, here we are using 3 coins. So out of this 2, we should output the minimum. What we will do, for all the paths that we are getting, we will choose minimum of both the case. Okay, and I'll explain that, okay, how these things are handled, especially when we are having negative amount, and especially when we are out of index. Okay, so in order to choose minimum, so what we will do is, whenever we are out of index or we have negative, we will tell it as infinity, that we will return infinity, because we know that if we take minimum between infinity and anything, right, then we'll always get that number. Okay, because infinity and minimum. Now what I mean is, for example, this will return infinity, okay, to its parent, and this will return 1, because we know that in order to make amount 2 with just coin 2, we need one coin. And we know that what's the minimum between infinity and 1? It's 1. So at the end, this parent will return 1. Okay. So we will see step by step how it goes. We already covered DFS. So this is the same approach of traversing the binary tree. That was a binary search tree, but the approach remains the same. It's a traversal of the tree. But let's go step by step. That will be best. Okay. So I'll show you again that what we have coded. Okay. We have coded these two approaches of tabulation already. Okay. We optimize just the space. So these are like just a tabulation approach, not two different approaches. But now it's time for recursive. I'll code this. Okay, let me remove that. And I'll code this. Okay, I removed also the default code. So let's not remove everything. Let's remove from this part. Oops. And in the interview, it's asked to code with all the approaches. And that's why I'm covering this. So firstly, what we have to do? We have to traverse like the tree. So we will go all the way down and then come up like we did for the DFS, or we can say binary search tree or in order traversal, pre-order traversal. We discussed all this stuff. But if you didn't watch through this video, it's fine. You will catch up here as well. So let's begin. Firstly, what we will need is a DFS function. Let's call it helper function. So as of now, let's not write anything. We'll come to this later. Let's have one helper function. We can also call it DFS, by the way. Doesn't matter. We will need these two arguments for sure. So let's put it. But what else we will need as an argument? What else we will need? We have to check just this tree. That we need these two things. Whatever current index I am at, if I don't choose, so current I start from index 0. If I don't choose, I go to index 1, right? And whatever is the amount right now, whenever we choose, we decrement the amount based on which coin we choose. So we need two things. Firstly, whatever index I am currently at, this will be also int, and how many coins are used. These two things we need. And also this will output int. So these two things are needed, and we know that if when we code recursion, we have two cases, base case and the logic. So these are the two cases. Now we always write logic first. So firstly, let's have not choose case. So it's a case 0. Let's call it case 0 when we don't choose. So that's the magic of recursion, that how you pass the iterative arguments and it looks like we are not using any looping, but at the end we are looping all the way down, right? This can be done iteratively using while loop or for loop, but this is the power of recursion, you can say. So coins will be needed, amount will be needed, and when we don't choose, right, then we go to next ID. So just write IDX plus 1. We go to the next coin, and coins used remains the same. Anyone amounts remains the same. When we don't choose, we can't change the amount. But if we choose, so this is how simple it is to write recursive. So it's, let's say, case 1. Again, let me copy paste. It's not the same thing. We have to change. So firstly, when we choose, what happens? Our amount will be reduced. By how much? If we choose, our amount will be reduced by whatever is the denomination of that coin that we choose. So amount should be reduced by, let me write, amount minus coins of whatever current IDX I am at. And since we can choose the same coin unlimited number of times, we are still at the same index. And obviously, coins used should be incremented by 1. And that's what we did. And as I said, at the end, we return minimum of case 0 and case 1. But the most important part is, I'll write on it, don't worry. What important part is the base case. When we stop. So we stop when we have negative amount, when we are out of index. So they are left with nothing. So it means our IDX went out of this coins list. and also when we stop when our amount is 0. But this is the valid case. Okay, these two are not the valid path. Not valid case, you can say valid path to make our amount 3. But these two are not the valid path when we are out of index and when we have negative amount. And negative indicates that you can't make other amount, right? By that particular coin. You can't make amount 3 with coin 2. And that's why it's suggesting is negative. So that's the mathematical way. But okay, sorry. So let's go here. That in the base case, first will be, sorry, if my amount becomes negative or my IDX is out of bounds. So when it becomes out of bounds, when it's equals to the length of the coin, because we know that index goes from 0 to length of coin minus 1. So when it hits length of coin, you can say we are out of bound. And in this case, we will return infinity. I mean, here infinity can be amount plus 1 as we already seen, but let's write infinity. Oops. And there is one more base case, and this is our valid path case. Then when this is 0, we just simply return whatever is the coins used until now. One more thing is still left, just a bit of an edge case. But let's run this and see the mistake of the edge case so that it's easy to understand. And we have to pass everything, coins, amount, but rest 2, that is IDX and coins used, we should start from 0. This will give us an error for sure. Yes, this is the error. That, and we know that using just the coin 2, we can't make amount 3. How many number of times we use, we can't make amount 3, right? So we have to handle that edge case. And what can be that edge case? That will be, this both will return infinity. Okay, so minimum of infinity and infinity, still infinity. And that's why we are getting, and we were told that when this such is the case, you should return -1. Expected is -1. It's written in the question that just return -1 if you cannot make using any combination. So that can be handled easily, that when my this function is returning something which is infinity, and our infinity here is amount plus 1, you can say that, or you can say greater than amount, right? Amount, we will, anything greater than amount will be infinity for us, and we know this because, for example, we have to make amount 12 using just the smallest coins which are 1, right, of one denomination. We will need 12 coins. We will never need the coins greater than the amount. And that's why if this is the case, then we will say just return -1. We can't make it. And else return the usual case. Let's run now. See, it's accepted. And obviously I know that if we will run, it will be time limit exceeded. Why? Because we are growing exponentially. And what will be the time complexity for this? Space complexity will be the recursive stack space. But what will be the time complexity? You can see we are getting time limit exceeded. It's not an error, code is working fine. But the time complexity will be 2 power. Every time we have two choices, n plus m, where n is length of the coin, m is the amount. Okay, so we are roughly, it will be exponential, you can say that. And this is not good, and that's why we are here. We did already tabulation, but now we have to do memoization. Now what memoization? It's nothing. We will be have the same, we will have the same time complexity. Okay, space we optimize in tabulation, but at the starting we got both, how much, mn and mn. I still have the code, you can see we got space both mn, mn, mn. At the end we optimize the space, but time still remains, because we have two for loops, right? So time still remains mn. In memoization, still time remains mn and space also remains mn. So you can use either of the method. Just I'm showing that there are two different methods, tabulation and memoization. So in memoization, what we do in the repeated subproblem, which is this one, 2 1, we store it in some data structure, and when we encounter that repeated subproblem here again, we use it from the data structure. So let's say we are using a dictionary, but before that, this memoization code is really simple if you can write recursive code, and that's why I showed this. Now this is really simple code, I mean bit tricky of course, so let me dry run that. So let's say we start with 0000. Okay, that's where we start with. So we are first calling this. Okay, if this is confusing, let me write this into result, and you can say if my result is infinity, then return this, else simply return the result. Let's assign. If it's confusing, you can do this way as well. Okay, if you run it will run. So rather than doing this in the base case, in most of the problems that we will encounter in DP, passing coins or whatever, like if we will see the minimum cost program, which we will see the very next one, then passing every time the minimum cost will be a bit problematic. We will see that. And that's why, because this kind of recursion is easy to understand, and that's why we use this. But okay, let me not remove this. Let's write on this first, that what is happening here. What's happening is, firstly we start with this. Okay, so immediately we are over here. Firstly, these two cases are not met, not amount is also not 0, so we will be at the not choose case. We come here at the not choose case. So what, at the end we are at this branch right now that we didn't choose. Okay, and now we incremented our idx by 1 since we are at the not choose case. Since we incremented, we are calling the same function again. So now idx becomes idx plus 1. Previously it was 0, now it's 1. Now we are coming here again, and now again coins remains the same, amount remains the same, because we are not in the not choose case. We didn't go further from the here, okay, because since we encounter here, we are calling the same function again. So again idx will be now 2. So firstly we are at here when idx becomes 1. Okay, this here it's idx become 1 because coin 2 is located at 1 index. That's why idx become 1. And we again encounter not choose case, then we are out of bound. What this blank indicates, it's like we are out of bounds. So idx became out of bound. So now we hit this base condition, one of them, okay, that my idx becomes coin, equals to coins. So what we will do, we will return infinity. So what will happen is, this will return infinity, that I am out of bound, sorry. So now I will go to the, since we have return statement now, so case 0 will be infinity, and now we are going to the next line, which is case 1. And we know this, why this is case 1, because we are choosing now. If we choose, then again, now right now we are at this flow. I want everyone to write on this in your head. I mean using pen and paper, of course. Now we are here, okay, but at this place, which is the choose case of this one. Now again, since we are choosing, we will reduce our amount. So we reduce from 3 to 1, and our coins used will also be increased. So previously it was 0, now our coins used became 1. Now again we have 2 branches, right? So, and we know this, why this, sorry, and we know this, why this 2 branches, because we are calling the same function again. So again, it will check any base condition if satisfied. No, it's not. So again, it will go in the not choose case, which is that not choose case, this one now. Okay. And this will hit the base case, okay, of infinity. So now it will return that not choose case of infinity here at the case 0. And then we will again go back to new. So again, the previous case 0 infinity, which was this case, right, this infinity is still stored in the stack. Okay, when we come back above, like, which we call it as a backtracking, when we come back after hitting the base case, we will use that case 0 and case 1 and then take the minimum to pass on. upwards. Okay, so this is how the entire flow works. Okay, so if you will write and you will get it, but I'll just show you the way that how this works. Okay, but in most problems, it's better to not pass every time this thing. Okay, and rather when my amount becomes 0, return 0. But obviously we have to modify something. So firstly, let's remove that. We don't need the last one here as well. Everything else remains the same. Just what we have to do, rather than passing as an argument, I will pass it here. Okay, that's it. I mean, I'm doing nothing extra. So these are two ways of writing recursion. Rather than tracking every time returning coins used, now I am using coins used plus one here only. Okay, every time my case one, I'm increasing by one. I mean, this recursion is a bit complicated to understand, but I gave you the flow now. So, and now using this memoization will be pretty simple. So what we will do, firstly, let's write. Now we have to do memoization. And we will use one dictionary for this. Let's call self.memo. And what will be the key and the value? Because everything what we store in the dictionary, every key should be unique. And we know this is a repeated subproblem, 2, 1 and 2, 1. So what is repeating, what should be the key, what is unique, that whatever index we are currently at, so don't consider it as a coin, whatever index we are currently at and how much amount we are left, this should be our unique key. Okay, so our key should be whatever index I am currently at, it should be combination of both, and how much amount we are still left. And what I'll do is, every time I'll store that if my key is already in memo, then I'll simply use that. Simply use and return self dot memo of that our key. And obviously, every time when we do this, we have to update our memo with that key as what should be the value. Obviously, it remains the same. What is the minimum? And here also, we should return. We can return minimum as well. It's the same, but better to return this thing. Let's run this. It's accepted. Sorry, perfect. Yeah, it's accepted. You can see. And let's check. Yeah, it's working. Now, if you will see the time complexity, it's still mn. So previously it was time limit exceeded, but now it's mn. So what I'm doing nothing. I'm just doing the same thing, but simply I'm storing it in the dictionary with a unique key. And how to identify that? If you don't know how to draw this tree, it's not possible to identify that unique key that is needed. Okay, so that's about memoization. And how much will be the space, if you will notice. And obviously I have to show one thing. I know that the video is a bit longer, but I apologize for that. So what I did is I also asked ChatGPT or DeepSeek to write on this, and you can see the if you write a good prompt, you can do it. So it starts with index 0, and we start with coin 1. We have the memo key right now. Firstly, we are skipping it. Okay, and we are just passing amount and IDX. Rather, I mean, in the original helper function, we have everything. Even they are passing memo, but I don't think we'll pass memo. We are using it to the as the parameter, but rest of the things remains the same. Okay, so we are taking the minimum of case 0 and case 1, and so we will start with what we need, the unique thing, right? Amount and index. Rest doesn't matter. That's why they didn't show here every time. This is the amount and the ID, and that's what matters, because rest of the arguments remains the same. And you will see that firstly skips. Okay, so we will call again the same function, but now as we skip, amount remains the same, but ID becomes 1. Okay? ID is incremented. Now this will be called, so again, memo is not yet updated because we haven't reached that point. Again, it will call itself. So we will go to this thing, and this will be later. Okay, we will go to this thing. Then this, after this, our idx becomes 2, which is out of bounds. So return infinity, right? So we are having no solution. Now we are backtracking. So now we are backtracking to one case, which was this one, right? So I'll just show you this entire thing, that how this entire dry run. I mean, I want you to dry run this in the chat GPT and or DeepSeek and use it. I found DeepSeek better in this case, at least. But you have a pro version of ChatGPT that can also be the better version. So if you let the end see how this recursive flow happens, this will be really easy to understand, and use this AI tools right now. I already showed you the flow, how to do this, but this will clear your mind if you'll carefully do this. So I'm not going through the entire thing again and again, but this is the way how to do this. And the space complexity, as I said, and why even I asked space complexity, and you can see why it's m cross n. If you notice that each state is defined by a unique key, right? And we know that our amount ranges from 0 to n, and our ID ranges from length of coins. Total unique subproblems will be n cross n. Okay, and we know that after we have calculated, we have to just look up. Okay? So final will be m cross n. Okay? Since we have to solve everything just once. And space, maximum n cross m. Why? Because maximum depth, what we'll have, firstly here, since we have amount cross ID, maximum entries will be n cross m. And the deepest recursion occurs when we take the smallest coins, which is 1, repeatedly. So the maximum depth will be O of n. So we have to do n recursive calls maximum. So we know that higher dominates, so it will be n cross n. So memoization dominates. So this is how you can utilize this AI tools. And this is how the memoization and recursive approach works. I know it's a bit overwhelming or it's a bit too much, but I think it's worth it, and hope you now do the DP problem with all the techniques that I showed you. Thank you.